How many times a day do we flip the switch to turn on the lights? Or plug our phones and computers into charge? Most of us use electricity every day, but how much do we know about it? My name's Valerie, and I'm the Outreach Coordinator for Future Energy Systems, or FES. FES is a research program at the University of Alberta that's focused on studying the energy transition. Thanks so much for joining us to learn about electricity and circuits in this series of clips where you'll get to try a bunch of experiments yourself. In this first part, with 3 easy-to-try experiments at home, you'll learn about atoms, electrons, electricity, and especially static electricity. Here are the supplies you'll need. Have fun!
Hello, my name is Leslie, and today we're going to be talking about electricity. So as we know, energy comes in many different forms, and electricity is just one of those. We pretty much use electricity every day of our lives.
From turning on the lights, to keeping our food in the fridge, to powering the computers you're using for school. So what is electricity? Electricity is a form of energy that involves the flow of electrons. Remember that everything around us is made of atoms, and atoms have protons that are positively charged, electrons that are negatively charged, and neutrons that are neutral. And the electrons revolve around the nucleus, which is made of the protons and the neutrons. Usually the number of protons is equal to the number of electrons, so the positive charges and the negative charges balances out. But sometimes when there's an outside force, the balance is destroyed and the atom might lose or gain electrons. So when atoms lose electrons, the electrons can start jumping to another atom. And this free movement of electrons is what causes an electric current. Sometimes electricity can be accidentally generated. For example, static electricity. Static electricity is a stationary charge. This means that it is a charge that is not moving and does not generate any current. It's generated when a surface or material has an imbalance of electric charges, usually from friction, and this charge will stay there until it has a chance to move to a different place. So what does it look like? Have you ever gone down the slide and your hair sticks to it, or your hair sticks to a balloon, or when you rub your feet on the carpet you can shock one of your friends? All of this is known as static electricity. When 2 objects are rubbed together, one of the objects gives up electrons and the other one gains the electrons. This means that one of them is now more positively charged while the other is more negatively charged. Now let's take a closer look at the objects. We know that like charges repel each other, so the 2 negative charges want to get as far away from each other as possible. So this is why your hair stands up when it's statically charged. Each of your hairs wants to be as far away from each other as they can. Then when you touch someone else or touch a piece of metal, you sometimes feel that shock before you even fully touch the other object. This is because you guys are creating a path for the electricity to reach the ground. You are closing the circuit, and this sudden discharge of energy is what creates the spark that we call a shock. Now, lightning is a great example of static electricity in nature. Basically, the water droplets in a cloud are rubbing together, and the friction causes a separation of charges where the positive charges line up at the top and the negative at the bottom. Now, on the Earth's surface, we have houses and buildings and trees, which have positive charges that can line up with the cloud. And if these charges get big enough, it can cause a sudden discharge of electrical energy so that the negative charge can connect with the positive charge, and the energy can reach the ground. Lightning wants to take the fastest route to the ground, which is why we construct tall lightning poles to protect the rest of our buildings from this static electricity. While static electricity can be dangerous, it can also be useful. Our photocopiers and laser printers use the principles behind static electricity to do their jobs.
Alright, so we're going to do 3 experiments to see this in action. But before starting, make sure you have your parent or guardian's permission. Okay guys, so for our first experiment, I'm going to show you how to move water without touching it. So what you're going to need, you're going to grab a balloon and go to your nearest sink. So you might want to ask your parent or guardian for a little help with this one, but come on, I'll show you. Okay, so as you can see, I'm with my sink. So the first step you're going to do is you're going to charge the balloon. So how we do that is you're just going to rub it in your hair until you kind of start seeing your hair stick to it. Rub it a little more and remember what side you rubbed your hair on. Okay, so now with your tap, you're going to turn it on just so it's a little stream. Something along that big is good. And you can ask your parents for help at this step. So what you're going to do is you're going to lift the tap up, and with your charged balloon, you're going to bring it close to the stream of water and watch what happens. Do you guys see the bend? So here I have a balloon that's not charged, so I didn't rub it on my hair. And let's see what happens when I bring it close to the stream. So nothing happens. So isn't that cool? We were able to move the water without ever even touching it. So why do you guys think that's possible?
So let's take a closer look at the three scenarios that we saw, with the water stream by itself, the charged balloon, and the non-charged balloon. So the water stream by itself has neutral water coming out it, meaning that the water has a balance of positive and negative charges in it. The charged balloon has excess negative charges near the surface. So when we put it close to the stream of water, the negative charges attract the positive charges in the water, and it kind of acts like a magnet. But when the balloon isn't charged, the balloon itself also has a balance of positive and negative charges. So when we put it near the water, nothing happens. For our balloon to pull the water towards it, it needs to have the extra negative charges near the surface.
All right, so for our second experiment, I'm going to show you how to make salt and pepper float in the air. So you're going to need to grab a plate, grab some pepper, grab some salt, and you need your trusty balloon here. So to start, I'm going to get you to mix some salt and pepper on this plate. So as you can see on this plate, we have a mixture of salt and pepper. Next, you're going to take your balloon and charge it. So really rub it on your hair until you kind of see your hair stick to it. That means the balloon is getting charged. And then, let's get this hair in control. When you place the balloon close to the plate without actually touching it, you can see the salt and pepper starting to float. So taking a closer look, I just added a box so that we can see it better. But when we bring our balloon close without touching the plate, you can hear it start to float up. See, we're picking up the salt and pepper without even touching it. And if you look on your balloon, you can see the salt and pepper sticking to it. So now, why do you think that happens?
Let's draw this out. So you have your plate, and you fill it with your salt and your pepper. And just like the water, the salt and pepper have balanced charges of protons and electrons. So altogether, they're neutral. Then, when we add our charged balloon that has excess electrons on the side of it, we start to pull up the salt and pepper by attracting their protons. Now, a question we can ask is, why is there more pepper than salt on the balloon? And the answer is simple. It's because the pepper is lighter. Now, if we imagine this is our piece of salt and this is our piece of pepper, Both have protons and electrons. However, the salt has more simply because it's bigger. So you can see that picking up pepper is easier than picking up salt, just like how picking up a small object with a magnet is easier than a larger object.
Okay, so for our final experiment, we're going to have a pop can race. So you can do this with someone else in your house, or you can time yourself and try and beat your score. But the catch is you can't actually touch the pop can. So what you're going to need is an empty pop can. Make sure that it's dry. I have my trusty finish line that I'm going to put at the end of my race. And then, of course, you're going to need your balloon. So you're going to place your pop can on its side, and then we're going to charge our balloon again. So rub it in your hair real good until it starts sticking to your hair. So maybe a little more. All right, so I think that's charged enough. And then watch what happens when I put the balloon close to the pop can. It starts coming towards it. And then, yay! Notice how I'm pulling the pop can instead of pushing it. So let's see it again. Why do you think that I can move the pop can with the balloon?
So again, let's draw out our neutral pop can, meaning that it has the same amount of protons and electrons. Then we can draw out our charged balloon that has extra electrons near the surface. Because of the attraction of the protons to the electrons, as we move our balloon towards the finish line, the pop can will be attracted and move with it.
So that's it for the experiments today. Let's recap. What did we learn? First, we learned about electricity as a form of energy, and we learned about static electricity. Atoms make up all the matter around us, and they have neutrons, protons, and electrons. When electrons move around, they can jump from one atom to another atom, and this creates what we call an electric current. And static electricity is a stationary electric charge that we can create with friction. Remember that one object gains the electrons and becomes more negatively charged, while the other loses its electrons and becomes more positively charged. And then we saw all of these principles in action. First, we made water move without even touching it. Second, we made salt and pepper float. And third, we were able to move a pop can. So make sure to try all these experiments at home, and you can share your pictures and videos on the Future Energy Systems Facebook page, and it'll be linked below. I'm excited to see what you do.
How did your experiment go? Was it hair-raising with your balloon to create static electricity? Now we're going to take what we learned about electricity and explore circuits. In this part, you're going to learn about how circuits work, the importance of insulators and conductors, and build your own circuit at home. Here are the supplies you'll need. Get lighting!
Today we're going to talk all about electrical circuits. Then I'm going to show you some super cool experiments. So we all know that electricity is super important to our lives. From charging our phones to turning on the lights, this is all made possible by electrical circuits. Remember that electricity is a form of energy that involves the flow of electrons. And this free movement of electrons is what we call an electrical current.
So what are circuits? A circuit is a pathway for the electrons to flow continuously. A circuit can be closed or it can be open, but only when it's closed is the flow of the current possible. When the circuit's open, there's a break somewhere in it and the flow isn't continuous. However, this is actually useful to us, and we'll come back to this later. Now, a simple circuit usually has 4 parts to it. The first one is a power source. So this is how we're going to give power to the circuit, for example, with a battery. Number 2 is conductors. These make the path for the electricity to flow, connecting the power source to the load, for example, wires. Number 3 is the load, and this is usually a light or a buzzer that's turned on when the circuit is closed.
And finally, we have a switch. This is to control when the circuit is open or closed. Remember when I said having an open circuit is also useful? This is so we can turn our circuit off at times. You don't want your light to be on forever. That would be a waste of electricity. Let's draw some circuits and see some examples. So how does this work? Let's start at looking at the power source. Batteries have a positive end and a negative end. This is so that the electrons have a direction to flow in. The electrons are negatively charged, so they're attractive to the positive charges. As such, the electrons will flow from the negative end of the battery through to the positive end. This electrical charge then flows through the conductors towards the light bulb and it powers it. The electric charges flow through the light bulb and continue through the wires all the way back to the battery. This is why we call it a circuit. The electricity will flow in a never-ending loop until we either flip the switch off and cause a break in the circuit, or the battery runs out of power. So here we saw a simple representation of circuits, but in real life they're much more complicated. Our homes get power through something called an electrical grid, which is basically a very large network of connections from power generating plants to our homes, and it brings us electricity. Have you ever lost power in your house and noticed that the entire neighborhood also lost power? It's because you guys are all powered by the same electrical grid.
Now, another concept we should go over is the difference between conductors and insulators.
In our circuits, the wires act as conductors and are able to transfer the electric charge. Conductors are basically any material that will allow electricity to flow through it. For example, metals such as gold, aluminum, or silver. Insulators, on the other hand, are used to stop the flow of electricity. They are made of materials that prevent the transfer of electrons. These protect us from electrical shocks, for example, wood or rubber.
Both conductors and insulators are really important. Let's take your phone charger, for example. The inside of the phone charger has wires that conduct electricity so that your phone can be charged. But the outside of the wire is covered in rubber so that it can stop the flow of electricity, so when you touch it, you don't get shocked every time. So now let's play a little game. I'm going to name a material, and then I'll give you 3 seconds to guess if it's a conductor or an insulator. Ready? Number 1, tinfoil. Number 2, diamonds. Number 3, a toothpick. Number 4, copper. Number 5, water.
This is actually a trick question. 100% pure water does not conduct electricity. However, tap water, rainwater, and most of the water we use does conduct electricity because it has other minerals in it, such as calcium and sodium ions.
All right, good job, guys. It looks like you have a good handle on electrical circuits, conductors, and insulators, so let's do some experiments to see this in action. For our first experiment, we're going to make our own circuits. So what you're going to need is a 9-volt battery, some strips of tinfoil, a little LED light, or what I have here is just a Christmas light that I cut off. And then this is optional, but you can get a paper clip and a little thumbtack. Plus, I'm going to be using some tape just to make sure our tinfoil doesn't move around. Okay, so let's build our circuit. So first with your tinfoil, you're just going to fold it into little strips like this. And over here I just have a pile of pre-folded tinfoil. Now, so we know for our circuit, the important parts are our light, our power source, and our switch. And then the tinfoil is going to act as our conductors or wires.
First, we're going to start with our light and use our tinfoil to connect it all the way until our battery. Somewhere in the circuit, you can create a small gap, which will act as a place for your switch.
I'm just going to stick this thumbtack through the tinfoil to keep the switch in place.
So let's be careful with this because it's really sharp. And then we're going to put our switch right on top of that thumbtack. Alright, so our circuit's going to look something like that. So I'm just going to take some tape and tape it down. So that's our finished circuit. So when I take this 9-volt battery and close the circuit, what do we think will happen? Let's see. Nothing. So why did nothing happen? Let's start at one side of our circuit. So we go all the way through, and we see this. Our switch is open right now. That means we have an open circuit. So when the electrons come to this little gap, they can't flow across to the other side. So when we close the circuit, let's try it again. Our light turns on.
Now you can continue to experiment with different circuits with multiple lights, multiple switches, and even multiple power sources.
Okay, so I'm going to show you guys something else really cool today. It's called the Makey machine. So this right here is the Makey machine itself. So the piano is our load and the laptop is acting as our power source. And everything in between is connected by conductors. And I'm acting like a switch. So every time I touch a conductor, I'm closing the circuit and we're going to be able to hear it. But if I touch something that doesn't conduct electricity, an insulator, it's not going to work. For example, a banana, a fork, even if I touch this cup of water, or another human. And then the light that we used from the other experiment also works. That's it for today. Thanks for listening. I hope you guys have a lot of fun making circuits at home.
How'd your experiment go? Were you able to complete your circuit and illuminate your light? Thanks so much for exploring electricity and circuits with us today. Make sure to subscribe to Future Energy Systems YouTube channel so you don't miss any of our exciting content, and check out the links below. There's so much to learn as we explore our energy future.